Hey, honors pre-calc. Today we're going to be learning lesson 2.2. This is the second of 7 lessons in unit 2. This lesson specifically is about polynomial functions of higher degree, and that's referring to lesson 1, which was about quadratic functions. So quadratic functions have a degree of 2. It means that 2 is the highest exponent on an x in the polynomial. So polynomial functions of higher degree, which we're doing today, means exponents greater than 2. So we might be looking at x cubed functions or x to the fourth. You can see in this what will you be able to do section. At the end of this lesson, you'll be able to determine the zeros and the end behavior of functions such as this, which is with a degree of 4 because it has a 4 as the highest exponent. What we're going to do today is students will understand the relationship between the degree and the leading coefficient of a polynomial to describe the end behavior of a function. That means what does it do as we go further to the left or further to the right? What's the end behavior at the ends of the function? Students will graph polynomial functions given the zeros and multiplicity. We'll talk about what multiplicity is. Students will apply the fundamental theorem of algebra to determine the number and type of zeros of a polynomial function. And the essential question today is, how can the zeros in a factored form of a polynomial function be used to describe the behavior of its graph? And all of this will become clear as we do a couple of examples. So I'm going to pause this really quick and get the notes ready. All right, so here are our notes. And the first definition is that a polynomial function has a graph that is continuous and only has smooth, rounded terms. So you can look down here before we actually get to this. You can see each of these is a polynomial graph because there are curves that are rounded. There are no corners. There are no holes either or breaks in the graph, so it's continuous. I could put my pen or pencil down and sketch the whole thing without lifting up my pen, okay? So that makes it continuous and smooth. A monomial is just x to the n. It's the simplest form of a polynomial function, right? Mono is a prefix that means 1, so it's just one term. The n is the exponent here, and the n is an integer that's greater than 0, right? An integer meaning a whole number that's positive, so 1, 2, 3, 4, etc. And today we're going to be studying how the evenness or oddness of that integer, of that exponent, kind of defines how the end behavior will work. And we'll talk more about that, about what that means. But first of all, if n is even, the graph acts similar to x squared. So here's our x squared graph. Remember, it's a quadratic. It has a parabola shape. And it doesn't mean that every even exponent is going to look just like this, but it will have similar end behavior, which we'll see down here in this chart. When n is odd, the graph acts similar to x cubed, meaning it goes up on one side and down on the other. Okay, so now let's look at this leading coefficient test. Given f of x equals ax to the n plus whatever, with n as the highest integer exponent, in other words, the degree, the graph's end behavior is as follows. So there's kind of 4 different situations that might happen. If n is odd, remember we said if n is odd, it's going to be similar to x cubed. And you can see that just like an x cubed graph, it's going to go up and on one side and down on the other. So there's 2 different things that might happen if n is odd. If a is positive, so the leading coefficient, the number in front of the x with the biggest exponent, if that coefficient is positive, so if n is odd and a is positive, then we have this first scenario. And this right here is really the key part. This is what we're going to have to be writing as we get to the worksheet and the examples. We're going to need to know what the end behavior is. You can see on this graph, the graph falls to the left and rises to the right. And in math language, this is how we write this. As x approaches negative infinity, so we break it down into the x and the y directions. So as x approaches negative infinity, so as we go to the left, the y values approach what? And in this first question, the y values approach negative infinity. So as the x gets negative, the y gets negative. We have to be able to break this down into its x and its y. So that's going to be really important as we keep going here. As the x gets negative, the y goes down. As the x goes to the right, the y goes up, right? So as x approaches positive infinity, the y approaches positive infinity. So you can see these dotted arrows here are kind of showing us that the general direction, but we have to be able to break it down into its x and its y. As x goes right, the y goes up. So as x approaches positive infinity, y approaches positive infinity. If a is negative, you might remember from our transformations lesson that the whole thing is going to flip. So that means that now as we go to the left, as x approaches negative infinity, the y goes up. And as x goes to positive infinity, the y goes down. So this flipped to this. All right, what's happening in the middle with all these curves, we don't know that based off of this test. There might be like 15 different humps in here. I don't know. We don't know. All we know is the end behavior, what's going to happen as we get to the edges. If n is even, so if we're dealing with a function that's going to behave similarly to x squared, that means that on the left and the right, the y direction is going to be the same. So as x approaches negative infinity and x approaches positive infinity, the y's are always going to approach positive infinity. In other words, they're always going to be going up as we get to the ends of the graph. That's when a is positive. If a is negative, the whole thing flips upside down. So now the left and the right are approaching a y value of negative infinity as x approaches negative or positive infinity. All right, so hopefully that makes sense. There's a couple other properties that we can write down here. For zeros, the graph has at most n real zeros. Remember, n was the degree or the highest exponent. So the graph has at most n real zeros. The degree tells you at the most real zeros that it can have. And turning points, the graph has at most n minus 1 turning points. And turning points meaning like the extrema. So like this is a turning point because it changes from decreasing to increasing. This is a turning point. This is a turning point. So this graph right here is actually a nice example. We have 1, 2, 3, 4 zeros. So this could be an x to the fourth graph. It could be bigger, but it's most likely x to the fourth. And there's 1, 2, 3 turning points where the graph changes direction. So you can see you have 4 zeros, 3 turning points. These at mosts are really important. It doesn't always work exactly that way, but that is a general concept, right? That's giving you the most. All right, so let's look at example 1 here. View the following functions on a graphing calculator. So let's take a look. Got my calculator here. All right, so I'm going to plug in negative x to the fifth. I look at the graph. We want to know, is this graph related to x squared or x cubed? And if I look back at my parent graphs here, I'm going to say it's more similar to x cubed than x squared, right? It definitely looks more like that one. It's going up in one direction and down in the other direction. So it's more related to x cubed. And what does the negative do to the graph? So the negative in front, if you remember from our transformation lesson, instead of going up on the right and down on the left, it swapped it. So it does an x-axis reflection. And that you can also see based off of the a being positive or negative in this chart up here, right? It flipped it over the x-axis. All right, let's take a look at this one. X plus 1 to the fourth. Is this graph related to x squared or x cubed? Well, let's take a look. X plus 1 to the fourth. And that definitely looks more like x squared, right? It goes up on the left and on the right. And if we want to know what this plus 1 does to the graph, it shifts it left 1 unit. Okay. So a little bit of review of transformation, but mostly we're going to be worrying about end behavior. That shift to the left didn't change the end behavior from going up on both sides. Let's take a look at the back. Example 2. Now we're looking at actual end behavior. We want to determine the end behavior of each function. And looking at the graph isn't even necessary for us to be able to figure this out. All we want to know is the a and the n. So think about that on the other side. We have this a x to the n power is our first term, right, with our highest exponent. And so let's figure out the a and the n in letter a. Okay, so the a is the leading coefficient, that's -1. The n is the exponent, the degree, and that's 3. But we care about if the degree is positive or, if the degree is even or odd, that's odd. And we care about if the leading coefficient is positive or negative, and that's negative. So on the other side of the page, if you think about A is negative and N is odd, N is odd, A is negative. So this is going to be our N behavior. So we're just going to write that down as our N behavior. So let's write that down. So we have as X approaches negative infinity, the Y or the f of X approaches infinity, and as X approaches infinity, f of X approaches negative infinity. So it's an odd exponent, so it's going to look similar to x cubed, but it's negative, so it's flipped upside down. So the end behavior is going to be something like that. That's an arrow. So you can see on the left, we're going up, on the right, we're going down. That's what this language means. Okay, as we're going left, we're going up. As we're going right, we're going down. Let's try that 2 more times. So for letter B, our A is 1 and our N is 4. So this time A is positive and N is even. Remember, we only care about very specific things. We care if N is even or odd, we care if A is positive or negative. And every N behavior starts with this same template. As X approaches negative infinity, f of X approaches something. As X approaches infinity, f of X approaches something, okay? And those are the blanks that we're trying to fill in each time. So here we are positive and even. So eventually we're gonna have to be able to do this without looking at the chart. So let's practice that. If we have an even power, it's gonna be similar to X squared, and A is positive, so it's not flipped upside down. So in other words, it's gonna be, the N behavior is gonna be similar to the X squared graph. So it's gonna be going up towards positive infinity on both ends, okay? One more over here. Same idea, we're looking for A, N, and we're gonna fill in this same fill in the blank N behavior model. So A is 1 and N is 5. So now we have an odd power and a positive coefficient. And so let me think about that. If we have an odd power, it's gonna be like a cubic, X cubed, and it's positive, so it's not flipped upside down. So it's gonna be going like this. And that means as we go to the left, we're going down. As we go to the right, we're going up, okay? All right, last example here, zeros. We know zeros. That means we set the function equal to 0 and solve for the values of the x's, because that's gonna be our x-intercepts or our zeros. So let's try that here. In this first one, we have 0 equals negative 2x to the 4th plus 2x squared. I'm going to factor out a negative 2x squared from each of these terms. And I am left with x squared minus 1. Yeah. And then x squared minus 1 can factor further to x plus 1, x minus 1. And okay, so let's see what we got here. In this lesson, what I would like us to do is if there's a 0 that repeats, we're going to write it multiple times. So this represents, since it's x squared, it represents that there's 2x equals 0 zeros. This is going to give us a negative 1 when we set it equal to 0, and this is going to give us a positive 1. So we have 4 zeros here, even though the 0 repeated. They're all real, and the leading exponent, or the degree, is 4, and we have 1, 2, 3, 4 zeros. So that made sense, right? That number 4 always equals the total zeros. It's just that some of them might be real and some of them might be imaginary. That's why we say that the number of real zeros is at most that number. So we got 4. I will also say at this point that whenever a 0 repeats, that's referred to as multiplicity. which is a word that comes up in the homework worksheet. So that's going to be important. So in this context of this problem, x equals 0 has a multiplicity of 2, meaning it's a 0 twice. It showed up twice. So if there's a 0 that has a multiplicity of 2, it means it showed up twice in the breakdown of the zeros. Okay, so let's try B and C. In this one, I'm going to factor out x cubed, and I'm left with 3x minus 4. So I have x cubed, which means I'm going to write x equals 0 3 times. And then I have 3x minus 4, so I'm going to write 3x minus 4 equals 0. 3x equals 4, so we have x equals 4 thirds. Okay, so this one, this time the 0 has a multiplicity of 3. And it's not something where like every question has there's one 0 that has multiplicity. Anything could be said to have multiplicity. So 4 thirds has a multiplicity of 1 here because it showed up once. All right, let's take a look at the last one. 0 equals negative 2x cubed plus 6x squared minus 4.5x. And I'm going to deal with that decimal right now and multiply everything by 2. So I can hopefully get rid of that. So I'm left with 0 equals negative 4x cubed plus 12x squared minus 9x. I'm going to factor out a negative x. And I'm left with 4x squared minus 12x plus 9. And that factors into 2x minus 3 and 2x minus 3. Okay, so that's fully factored. We have x equals 0 once this time. And this time, between these two factors, we get x equals 3 halves 2 different times. So you could say that the 0 of 3 halves has a multiplicity of 2 because it showed up twice. All right, so that's the end of the notes. If we take a look briefly at this worksheet, I wanted to point out at least one thing here. So this is the 2.2 practice worksheet that you have. Number 2, the end behavior is a trick. Okay, this is going to test you because take a look at this graph. For most polynomials, or really any type of function that's here, the curve either goes up towards infinity or down towards negative infinity as you get towards the end points of x, right? As we look at the end behavior. This one has a straight line. So notice that instead of having an arrow here, it's like f of x is approaching something, it's in this question, it's f of x equals something. So the question I want you to think about when you're doing number 2 is, as we get towards negative infinity in the x direction, what is the value of y? That's what goes in this blank. It's just a number, right? It's not going to be infinity or negative infinity. What y value are we at as x gets close to negative infinity? And same thing as x gets close to positive infinity, what y value are we stuck at, okay? That's what's going on there. When it says increasing, decreasing, or constant, it wants to know the intervals in interval notation. So in this first question, it's increasing until an x value of 0. So we would write negative infinity to 0. Then it's decreasing from 0 to 2. And then from 2 on, it's increasing again. So that will go back up here. There's no interval where we just have a horizontal line, where we have a constant in this first one. So that doesn't exist, okay? On the back, yeah, you should be good with this. All right, think about end behavior, number of turning points, and zeros as you're doing this matching section. Hopefully that won't take you too long. All right, so that's it. Thank you for watching, and good luck with the worksheet. Let me know if you have any questions. Thank you.